A strongly connected graph is one in which there's a path from every node to every other node. Consider this graph on the top left. We can reach node C from A by starting at A, going to B, and then going to C over those edges. Here it is on the graph itself, A to B and B to C. We can also find a path from C to B through A. And it turns out we can find a path from any node to any other node. So this graph is strongly connected. The next to its right is also strongly connected, though it may not look quite so much so. So we can find a path from A to D by going from A to B to D. So A to B, B to D. Similarly with D to B and so on. What about C? Well, we have a path from C to A and to B and to D. So we have a path from C to any other node, and similarly any other node can reach C. So this graph is also strongly connected. What about the graph here? We have A, B, C, and D again. Is it strongly connected? And we can show by example that it is not. Try to find a path from, say, C to D. Well, we can go from C to, well, we can't go anywhere from C. So it is not strongly connected. However, it has strongly connected components. So if we take a subgraph, let me change the color here, that subgraph there, A, B, and D, that subgraph is strongly connected. And this is also strongly connected because it's just itself. So this is called a strongly connected component of graph G. And so the topic of this video is to talk about how we can split a graph, a directed graph, up into its strongly connected components. So we're going to start with the graph G. So here's an example, and we're going to do a depth first traversal. So let's start at A, and let me change colors here. We'll start with discovery time 1, and we'll follow the only path out that it has. So we get a discovery time of 2 here, and let's say we go in alphabetical order, so discovery time 3, and we cross that path, discovery time of 4. E has only one outgoing edge, that goes back to C, which is gray, it's been visited already, so we finish E. Then we return back to C, and it has no other outgoing edges, so we finish C. We return back to B, and it has one outgoing edge to an unvisited vertex, so that's D, and D can't go anywhere, so we close it off, we finish it, then we finish B and finish A. Okay, so that's the depth first traversal of this graph. Next, the next step is fascinating actually. We take the transpose of G. What's the transpose of a graph? The transpose of a directed graph is obtained by simply flipping all the edges, the direction of all of the edges. So you can see the edge from A to B in graph G, and the transpose is from B to A. Show that. So A to B and B to A. Okay, so now what we're going to do on the transpose graph is we're going to do another depth first search in reverse order of finish time. So the finish time in the original search, the greatest finish time is node A with a finish time of 10. So we'll start with A again, and we'll traverse this edge to D, and then we'll traverse this edge to B. B has nowhere to go. Well, it can go to A, but A has already been visited. So we finish B, finish D, and finish A. Now the next node with the next lowest or next highest finish time is C. We'll cross this edge, and E has nowhere to go. Finish off E, and finish off C. Now, what we have is a set of edges that we visited in the tree. So we take the depth first tree, and that leaves us with exactly 2 connected graphs. That graph and that graph. And those are the strongly connected components of the original graph. Now, let's go back and change my color here. Let's go back to the original graph. Well, that graph right there. And let's outline the strongly connected components. And let's make sure that they are strongly connected. So consider node D, it can reach B like that and there, and crossing those 2 edges. And similarly with A and B can reach any other vertex in that strongly connected component. And similarly in the other connected component, C can reach E and E can reach C. So we have 2 strongly connected components here. Now, here's the algorithm that's given in the book, and we're gonna and it says basically what we've been saying. We run a depth first search, and what we're looking for are the finish times. That's what we care about. Then we compute the transpose by flipping the edge directions. Then we run DFS, but the main loop we're going to consider in order of decreasing finish time, as we did before. Let's do another example. Let's start on this graph with, say, vertex E. And we'll cross that edge to F, and then we'll cross an edge to G, and then we'll cross that edge to H. H has nowhere to go, 5. G has nowhere to go, 6. F, and E. Okay, so now we restart the search, let's say at D, and we'll cross this edge to B, and B has 1 outgoing edge, and that goes to A, and all vertices have been visited, so we finish off A, we finish off B. Now D has 1 more outgoing edge to C, and there we go. Okay, so we've done our depth first search. We have those finish times, which is what we needed. Now here is the transpose of the graph, and we're going to run the same search, except we're going to do it in order of decreasing finish time. So we'll start at D, then we'll visit A. A will visit B. B visits C. C has nowhere to go. We finish that off. We finish off B. We finish off A. 6, 7, right? Okay. And then we finish off D. Then we'll restart our search. The next highest Finish time is E. And we'll cross this edge to G, cross this edge to F, finish that. And then we take care of H. Now if we mark every edge that we crossed, or the depth first search tree, we get this. And so we have, move this a little bit. A strongly connected component here, one here, and one there.